Today's lecture is going to be on some weather basics. We're going to be connecting sunlight, heat, and water, and kind of how they all come together and help us influence and generally influences the weather on Earth. So let's start off with the Earth's atmosphere. Here we've got our four primary named layers. If we talk about kind of the outermost part of our atmosphere and kind of work our way into the troposphere, we'd start off with the ionosphere. Sometimes it's referred to as the thermosphere. And this is where we can find auroras. Where we have the mesosphere, this is where meteors burn up in this layer. It's where we might see a shooting star. It's simply just a thicker layer of atmosphere. Then we move into our stratosphere. Stratosphere is what contains ozone, right? Ozone's a very important layer. It kind of absorbs dangerous ultraviolet radiation. And last but not least, the troposphere. This is our primary focus. This is where 99% of all weather takes place here in the troposphere. This is where life exists, life as we know it. This is where our atmosphere consists of roughly 78% nitrogen, 21% oxygen, some argon, and some trace gases. But notice some of those gases are what we're going to refer to as water vapor. Water vapor is a gas, a component of our atmosphere. So we're going to, even though it's a tiny percentage, this is the water in our atmosphere is going to be a primary player in weather conditions and factors. So here it goes. So what is weather? Well, weather is what the immediate conditions of our atmosphere are. Weather is basically the way the atmosphere is behaving, like right here, right now, mainly with respect to its effects upon life and human activities. Weather can change from minute to minute, day to day, seasonally, with a wide range of variability. But weather terms that we will look at in this class can be, we're going to talk temperature, right? That's kind of the obvious. All right, what's the temperature going to be today? Humidity. Humidity is going to be a feature that we will study in depth. Humidity is a very important, kind of an undervalued piece. Precipitation, it's always important to know, right? Is it going to rain? Is it going to snow? We're going to get some funky weather, sleet, hail, etc. Cloudiness, right? Another way you could refer to this is be how much sun. We could talk about, well, how bright is it outside? And what's the visibility? If it's foggy, we're going to have a different amount of visibility. We can talk wind speed, wind direction, right? The wind direction, winds out of the north are generally going to bring colder air with it. Winds out of the south are going to bring generally warmer conditions with it. And then lastly, atmospheric pressure. So all of these together are ways or terms that help us make sense of what the state of the atmosphere in our immediate area. So what is the weather like today? The dog asks. Well, just look outside the window. That's the weather. That's your weather going on right here, right now. Weather depends on where you are. It's always in a state of changing conditions. That doesn't mean that you can't have conditions that are relatively constant, but you've got air that's moving. You have moisture that's going to be changing. You have different degrees and amounts of sunlight. So there's a lot of variables in play here. That's what makes meteorology so fascinating, because there's no one way to answer, right? What's the weather like today? Well, where are you? Where are you, and what are the conditions going outside your window? So here's a graphic to the right that indicates warm weather that occurred in the Midwest for a 3-month period. That there's several locations that have temperature anomalies that range from 4 to 6 degrees Fahrenheit above average conditions. And there's a few locations that were slightly below average conditions. But this is kind of a 3-month or an extended time weather map. It's simply talking about the conditions, and this would be a temperature based on a little bit of over a greater distance than, say, just one day. So a few months. And therefore a general weather map is going to be something we'll look at. We'll look at a lot of weather maps. We're going to be looking at what the H and the L, right? High and low pressure. Pressure is going to be an important driver of how wind is going to move, how air is going to move, these air masses. And then we've got frontal boundaries. We've got cold and warm fronts that we'll be looking at. Here's a very defined cold front, and here's a warm front, the red. Here's another warm front. Here's another warm front. So we're going to need to make sense of these, including these lines. These are, pressure, barometric pressure maps. So we're going to need to be able to learn some real basic material to be able to apply them to different types of maps. I do want to make sure we differentiate between weather and climate. Climate is kind of how the atmosphere behaves over long periods of time, right? We're talking about a 30 to 100 year period, versus weather is kind of the immediate conditions. That the sun warms the equator. If I look at this map here, I'm kind of making sense of this. the equator more than the poles due to the angle of incidence, kind of the average angle of incidence, and insolation over the equatorial latitudes. Climate follows the general warmer pattern. Weather can be completely different than the general climate pattern, so understand that. The climate is going to be longer duration averages. Weather is immediate, like right here, right now, today. That regional climates can vary based on elevation, location or proximity to water, latitude, the terrain, the season, etc. So regional climates are going to have a much broader range of variability, but on average they have an acceptable range of what we would consider somewhat normal conditions. And therefore, let's not forget that the sun is the driver, right? Insolation or solar radiation, incoming solar radiation, is the driver of weather. That if we look at the total amount of sunlight that's entering our atmosphere, we would say that 30% gets lost back into space, reflection and scattering, right? 30% is kind of headed back where it came from. Whereas 20% gets absorbed directly by the atmosphere, right? Could be absorbed from cloud, from the atmosphere, from the gases themselves, from greenhouse gases, etc. Yet 50% is absorbed by the Earth's surface, right? Both land and water. And this is key. This is where the heat that's going to influence our tropospheric thermocline are going to come from. Our atmosphere is probably easiest thought of as heating from the ground up. So as we rise move upward in elevation or altitude, we would be experiencing a cooling effect, right? The further we are from the Earth's surface. This is what's heating. As you get further from that, it's going to get cooler. So remember that Earth's weather is driven by the heat energy from the sun and then water vapor in the atmosphere. And this is going to be key. This is how we're going to get clouds. This is how we're going to get precipitation. This is how we're going to come to the ingredients of severe weather when we get there. That the Earth continues to absorb visible light, right? That's what we're seeing here. Visible light's being absorbed, but re-emitted as infrared. That's that heat energy that gets trapped in our atmosphere. And that's not a bad thing, right? The greenhouse effect isn't a bad thing. That of the 70% of the heat energy entering the Earth's atmosphere, right, 50%, which is 71% of the total heat, comes from the heating of the Earth's surface. So this is key here. That we have the sun, we have our atmospheric gases, including greenhouse gases, and we have water vapor. These are going to be some of the fuel for what we talk about for weather. Let's make sure we state the obvious that land and water heat up differently. Right? Our planet's covered with roughly 70% water, 30% land. Water absorbs vast amounts of energy from the sun. Likewise, bodies of water release energy very slowly. For this reason, areas near water are usually more mild. Because of a water's ability to absorb heat, store it, and release it later, the oceans of the Earth have an important role in helping moderate the Earth's temperature. So we need to make sure we take what we study here and understand that the oceans are drivers of weather. We could also throw in the idea of climate as well, but we could talk weather. This is where our water is going to come from. This is where temperature stabilizers are going to come from. This is where winds are going to come from, etc. So land and water have different specific heats. They're going to heat up differently. Notice that the Earth's oceans are what transfer heat. They transfer heat in these ocean currents. We'll get to that in a minute. The oceans of the Earth transfer the heat. They're absorbing insolation, right? Incoming solar radiation from one location, and they transport it via these massive ocean currents elsewhere. So we've got our Pacific Ocean, we have our Atlantic Ocean, we have our Indian Ocean, we have our Arctic Ocean, we have our Southern Ocean, and really these are constantly moving. They're moving as they are transferring heat energy with the surface currents. And these currents are like rivers, right? They're flowing across the vastness of the Earth, bringing warm water from the equator towards higher latitudes, and cooler waters flowing from the high latitudes towards the equator. So it's this constant cycling of warm and cold water, which is really transferring heat or lack thereof. Cold water from our high latitudes, from our poles, moves towards the equator. And warm water from the equator moves towards the poles. So really, we can look at the oceans like they're a thermostat. And let's not forget the greenhouse effect, that visible light enters our atmosphere after being absorbed by the Earth's surface. Infrared, or long-wave radiation, heats the air above the land or the water via conduction, right? That's direct contact. That much of the long wave, the infrared energy, heats and gets trapped by our atmosphere, right? The gases, GHGs, our greenhouse gases, carbon dioxide, water vapor, and methane, CH4. that this heat provides the necessary temperatures to maintain water at the surface, driving complex chemical reactions for life. Right, so just a depiction that's the light energy entering. Well, not all of it is lost into space. Some of it is kind of trapped in here from greenhouse gases. That's not necessarily a bad thing. We like those comfortable conditions, and we definitely need liquid water. But now we're going to talk about the heat energy within the different forms of water, vapor, liquid. It's liquid in gases, and it's called latent heat. With the help of water, the Earth's atmosphere has the ability to store heat. But I do want to make sure we understand it's nowhere near the heat energy stored in the oceans. Oceans are dramatically more significant. But when heat is stored, it is referred to as latent heat. As water evaporates off the surface of a lake, this stored heat is carried into the atmosphere. As water condenses, forming raindrops, this heat is returned back to the Earth's atmosphere. It is this very heat energy that drives weather. And we're going to start referring to latent heat. It's going to become part of our daily conversations. And the latent heat is a part of the water cycle, right? As most other substances, water exists in three states: solid, liquid, and gas. The gas we call water vapor. The liquid form, don't overthink this, we call it water. The liquid. Ice is our solid. So even though the water vapor produced by evaporation, right, the atmospheric water vapor itself, it only makes up a very small percentage of our troposphere. It's an important atmospheric gas because it forms an important part of the hydrologic cycle that keeps the biosphere on the Earth's surface alive, right? This is the water that we need. We need the water in the troposphere. And so if we look at the distribution of Earth's water, realize that fresh water is only a tiny percentage. And if we subdivide fresh water, right, so the total global water here, oceans, roughly 96.5% of the total water. And if I subdivide my fresh water, just that tiny 2.5%, you see that a lot of that is glacial ice or frozen in the solid form. And some of that's groundwater. And then here we have surface water. And now notice that I'm even subdividing this. So of the 2.5% of fresh water, it's only 1.3% of that. And then of that 1.3%, now we actually have this tiny amount of atmospheric water, right? We call this water vapor here. That the atmospheric water vapor content, what we'll start referring to as WVC, water vapor content, is only 0.22% of Earth's water reserves, but is a critical component to weather, particularly severe weather and storms. And really that's where we're going to take this to. Find the water vapor content, which is what we're going to be doing studying relative humidity. So here's where everything heats up. The water vapor content is what we are going to be studying. Essentially, we're going to be asking the question, how much water, right? How much water vapor is in the air? So water vapor is the single most important gas in the atmosphere when it comes to understanding atmospheric processes, in this case, weather. That water vapor content, WVC, is the amount of water vapor in the air at a defined temperature. We're not going to be considering pressure here. So let's look at this table 8-2, and you're going to need to get used to this. This is going to be something we go to a lot, people. Table 8-2 simply says that warmer air, right? This is degrees C. Here's degrees Fahrenheit. Here's my capacity. This is the amount of water vapor can hold, can store. That warmer air can hold more water vapor, and colder air holds less. So we're going to make sure that we understand that relative humidity is a ratio of the air's actual water vapor content and the amount required for saturation or capacity, right? In other words, how much it can hold. That the capacity or saturation is the maximum amount of water vapor that a parcel of air can hold. And that's what we're looking at here. So we can calculate relative humidity is going to equal the water vapor content, right? How much vapor is in the air compared to how much it can hold, right? That's its capacity times 100%. And that's what we'll get. Relative humidity is a percentage. It's simply a ratio of how much it has versus how much it can hold. So here we see we're going to be using what we'll call dry bulbs and wet bulbs. So we're going to find the relative humidity of the air inside our classroom, and then we'll go outside and do this as well. And you're going to need to use this table here. This is our relative humidity calculator. We have a dry bulb that we'll call simply the air temperature, and we have what's called the depression of the wet bulb. So the dry bulb is the actual air temperature. You simply turn the thermometer on, boom, got it. And then you have a wet bulb temperature. After adding a wet paper towel, we can see that evaporation decreases the temperature reading. And we can actually do this here. And so you can see that if you pause this, you'll see that here's the temperatures from class. And you'll find that in the classroom at 22 degrees C, our wet bulb temperature is 11, had a relative humidity of 21% simply by finding 22 over